Oh, when we're very young and learning to tell the time, we learn that 5 hours after 10 o'clock, it's 3 o'clock. So in some sense, 10 plus 5 equals 3. Well, that sense is called mod 12 arithmetic, or modular arithmetic with a modulus of 12. Unfortunately, modular arithmetic doesn't reappear in English schools until further maths A level, which not many people do, and it's right at the end of their school career, even if they do. And so I find myself talking about it quite a lot because it's great fun, it's interesting, it connects to all sorts of other bits of mathematics, and it has some very useful applications. So that's what I'm talking about. I shall talk about modular arithmetic in general and about one particular application that I'm rather fond of, which is checksums. So the last digit on a bank card is a checksum, and I shall explain what that means and what it's for. It's quite different from the other digits. So let's get started. I'm going to start with mod 10 arithmetic because the underlying sums are easier. So suppose I gave you two numbers to add up, but I only told you the last digits of each. Well, then you'd certainly be able to tell me the last digit of the answer, wouldn't you? Because, well, 7 plus 9 is 16. So whatever's going on over here, this is going to be a 6. You can also subtract because 17 minus 9 is 8. So again, whatever's going on over here, that's going to be an 8. And you can multiply because 7 9 is 63. Okay, so that allows us to create a little world in which there are only 10 numbers. And here they are. And you can add them and multiply them according to these tables. So this table, for example, means that 7 plus 9 equals 6. And 7 times 9 equals 3. Now, this little world is called arithmetic mod 10. It's often notated Z10. And that contrasts with Z, which is often used for the integers positive and negative. So if we take a fact from Z10, such as 7 plus 6 equals 3, well, it is a fact in Z10, but it reflects a fact in Z, namely that a number ending in 7 plus a number ending in 6 is a number ending in 3. Well, it is for positive numbers. That's not really quite good enough. So let's extend that relationship to negative numbers before we come back and look at these in a bit more detail. And that requires the notion of congruence. So we have two integers, and let's say integers members of Z, and they differ by a multiple of 10, then they are said to be congruent mod 10, and it's written this way. So for example, all these numbers here are congruent mod 10. If you take any two of them and subtract one from t'other, you get a multiple of 10. In fact, there's a whole string of these, isn't there? All the positive numbers ending in 3 and all the negative numbers ending in 7 are in the same congruency class, as it's called. So they're all numbers that you can think of as being 3 to the right of a multiple of 10 on the number line, or they're of the form 10x plus 3. And this gives rise to a map from Z to Z10. So every integer in Z is congruent mod 10 to one of these. And this creates a map from Z to Z10 called reduction mod 10. So here's Z, which of course goes on forever, and here's Z10, which doesn't, it stops here. So this reduction mod 10 map is this. So all these numbers here map to 7, all these map to 6. And if you add any one of these to any one of those, you're going to get one of these, just as if you add that to that, you get that. If I might just raise the level of abstraction temporarily, these 7s are actually different. So just as there are more than one person called Jim Simon, there's more than one number called 7. This one here is a member of Z. It's an integer, a counting number. You met it first when you learned to count. And if you have two of those and add them together, you get 14. This one is one of these numbers, a member of Z10. And if you have two of those and add them together, you get 4. This 4, not that one. And technically, you can't really add that 7 to that 7 because they're just incompatible. So it's a bit like trying to add 7 meters to 7 kilograms. It just doesn't make any sense. Okay, so what this fact in Z10 is saying is A, it's a fact in Z10, 7 plus 6 is equal to 3 in Z10. And it's saying that in Z, any number congruent to 7 plus any number congruent to 6 is equal to a number that's congruent to 3. And if we put this reduction mod 10 business in, that's these numbers all reduce to 7, these all reduce to 6, and these all reduce to 3. So if we have any old integers here, we can either add them as integers and then reduce mod 10, or we can reduce them separately to Z10 and then add them in Z10. And we get the same answer. And the same is true for multiplication. Okay, so now back to these tables. We'll start with the addition one. It's a very simple structure, isn't it? You can see that in each row, the numbers go up by 1 until they hit 9, then they jump down to 0 and carry on up. That gives rise to this diagonal of zeros here. And crucially, it means that in every row, there's one of each number. And I say crucial because that's what enables us to do subtraction. So suppose we wanted to work out what 7 minus 9 is in Z10. Well, we want to know what we have to add to 9 to get 7. So we look along the 9 row until we see 7. And then we see that it's 8 that we have to add to 9 to get 7. And so 7 minus 9 is 8. So subtraction works because each row has one of each number in them. In particular, you can subtract from 0. 1 and 9 make 0, 2 and 8, 3 and 7, and so on. These, of course, are the number bonds to 10, but here we're thinking of them as within Z10, they add to 0. So there are no negative numbers here. Negative 3 isn't one of the numbers here, it's only 0 to 9. And yet there is a sense in which these two numbers are the negatives of one another. So I write this, but I'm going to pronounce this minus 3, not negative 3. It's short for 0 minus 3, or if you like, it's not the number negative 3, it's the number 3 operated on with the minus sign. So this 7 is minus 3 and 3 is minus 7. So there are no negative numbers, but every number has a negative. Okay, now we knew all along we weren't going to be able to do division here. So now we can see quite clearly why not. So the rows here are very far from having one of each value in them, aren't there? So this row is only even numbers. In fact, all the even rows have only even numbers in them. And this row is even worse. It's only got noughts and fives. So there really isn't any hope for doing division in Z10. Well, except 3. So 3 is interesting. This does have one of each number in it, and so does 7. And that, of course, is because 3 and 7 are co-prime to 10. They have no factor in common with 10. So if you look at the 2, the numbers go up by 2, and then they go from 8 back to 0 and then go round again. Whereas for 3, they don't get back to the start until they've gone right the way along. So you get up to 9, then down to 2, up to 8, and down to 1, and up to 7 before we get back to 0, essentially. So you can sort of divide by 3, and yet that'll be important later. Back to addition. So all addition tables look the same. It doesn't have to be 10, of course. We met Z12 very briefly right at the beginning. Here's Z7. It's very similar. This diagonal of zeros here. Every row has one of each number going up by 1. It's just the same. So let's look at some examples of all this. So we've met this one already. It's 3 o'clock now. What time was it 5 hours ago? We've now got 2 ways we can express that. We can work in Z12 and say that 3 minus 5 is 10. Or we can work in Z and say, well, 3 minus 5 is negative 2, which is a number in Z, and negative 2 is congruent to 10 mod 12. And it happens to be 10 that we write on our clocks, not negative 2. Then negative 2 would be a perfectly good alternative. Okay, here's another example. It's Sunday in a 31-day month. What day of the week will the same date be next month? So in other words, we want to work out what day of the week it'll be 31 days after Sunday. Well, 31 is congruent to 3 mod 7, and 3 days after Sunday is Wednesday. How much change do I offer? £20 note for 1947? Well, it's 53 pence, of course. And one way to think about that is that 53 is minus 47 in Z100. In fact, in any financial transaction, the pennies work in Z100. So you can work the pennies out separately, if you like, as long as you're not dividing. Last one. So it's 1817 in table tennis. Is it time to change ends? Well, you changed ends in table tennis every 5 points. So when the sum of the 2 scores is divisible by 5, you change ends. So yes, you do here. In Z, you can say, well, 18 plus 17 is 35, which is congruent to 0 mod 5, which is just a fancy way of saying it's divisible by 5. Or we can work in Z10, which is actually my favorite way of doing it, and say that 8 plus 7 is 5 in Z10. And once you've remembered that, that deals with not only the 8-7, but also 18-7 and 8-17 and 18-17. Those are all times when you change ends. Okay, back to multiplication. Now, multiplication tables are not all the same. So let's look at mod 7 now, multiplication. Now I've grayed out the zeros because it's the stuff in the middle that's more interesting. Now here we see that there is one of each number in each row, quite unlike the 10 example. You can sort of see why that is. There won't be any zeros in the middle because 7 is a prime, so you can't have two numbers less than 7 multiplying together, give a multiple of 7. And similarly, you can't have two the same in any row, because supposing you had, say, these two the same numbers, then that would mean 3 times 2 is equal to 3 times 4, which means the difference would be 3 times 4 minus 2, which is 2. And you can't have that being 0. So you can't ever have two the same. So you do have one of each number in each row, and that means you can do division. So for example, 1 times 1 is 1. If you look for the ones here, 2 times 4 is 1. So 4 is sort of like a half, and 5 is a third, and 2 is a quarter, and 3 is a fifth, and of course 6 is a sixth. So you can divide by anything by multiplying by its reciprocal. And of course, that'll work for any prime. So here's 11, and although it's quite a complicated thing, you can see that, again, there are no zeros in the middle, and each row has one of each number. And that's just because 11 is prime. So there are some rules we can work out for how arithmetic works in ZP, for any prime P. So we can add x plus y and get the same as y plus x. That's called, it's commutative. It's associative. X plus y plus z is the same as equals y plus z. There's a 0, which if you add it to something makes no difference. And for every x, there's a minus x, such that x plus minus x is 0. And the multiplication works almost exactly the same way. It's commutative, it's associative. There's a unit, x times 1 is x for every x. And for every x that isn't 0, there's an x to the minus 1, such that x times x to the minus 1 is 1. And multiplication and addition are related by this rule, the distributive rule. Now, we can work out that all the, apart from this one, we can work out that all of these are true because they're true of the integers. And that reduction mod P business will find an easy way of showing that all these are true. These then add up to making ZP a field. So these are the axioms for a thing called a field, which is a widely studied phenomenon. Integers are not a field, of course. The real numbers are, and the complex numbers are, if you've met those, and the rational numbers are. So ZP behaves very much like one of those. Exactly the same sort of calculations can be made as can be made in those fields. Of course, ZP is a finite field, which makes it rather special. It's only got P elements. And finite fields are very interesting, even when the prime is 2. So here we are. Here's addition in Z2, and here's multiplication in Z2. Now, I told a little lie right at the beginning. I said that modular arithmetic doesn't reappear until further maths A level. Actually, that's not quite true. Here, you may not have seen these tables before, but you certainly know the facts that they represent. So an even number plus an odd number is an odd number, for example. Let me rephrase that in the language you've just learned. A number congruent to 0 mod 2 plus a number congruent to 1 mod 2 is a number congruent to 1 mod 2. And that's a statement in Z that corresponds to this statement in Z2, that 0 plus 1 equals 1. Okay, right. Now, let's get this stuff to do something useful for us. I said that was a checksum. What does that mean? Well, suppose I were going to make a purchase online and I type my card number into the website. What's the website going to do with it? Well, the first few numbers will tell it what bank issued the card. So it'll look that up in some huge database, and let's say it's the National Bank of Baluchistan. Then it will send a message to the National Bank of Baluchistan saying, is this card one of yours? Does it correspond to a chap called Jim Simons? And is it good for an £18.50 purchase? Well, it would be a pity to do all that if in fact I'd mistyped the number. So it would be rather nice if there was a concept of an invalid card number that could quickly be checked, with the property that if I mistype my card number, it's very likely that the result will be invalid, in which case the website can come back to me straight away and say, no, that's an invalid number, try again. Well, it turns out it's possible to do that with just one extra digit. So, and it's called a checksum. So this is a very simple checksum. This is not the one that's done on the bank card. We'll come to that later. So what we do here is, the first 15 digits then are sort of my account number, really. And this one is just calculated according to this rule here, which is just to add up all the others mod 10. So when the bank issues the card, it works out what my account number is going to be and then just calculates P. Now, let's see how that works. So that's my 15-digit account number, and that's the checksum. Now then, that means, of course, that if I type in a completely random string into the website, it'll be a valid number 10% of the time. So it'll catch 90% of mistakes that way, which is okay, but it's not good. But if you design a good checksum, then you should design it so that most of the common mistakes that people make when typing in numbers create an invalid number. And then you can get much, much more than 90% of errors. So by far the commonest mistake that people make is simply to mistype one of the numbers. So let's suppose I mistype this 7. Well, as something else. Well, the other 14 numbers must add up to 1 mod 10, mustn't they? Because when we add that 7, we get 8. So if I type something else other than 7, the website's going to add up all these numbers, and it's going to up with 1 plus whatever I typed here, which is not going to be 8. So it's not going to check. So, and that works for any of these numbers, of course. So any of these numbers, if I mistype them, this is not going to check. So actually that catches an awful lot of mistakes. So this checksum detects all single-digit errors. Well, that's good, but we can do even better. The next most common error that people make is to type two numbers transposed. So as it were, to type 8-7 instead of 7-8 here. So now let's look at a real checksum. So this is the checksum in the 13-digit ISBN. That's International Standard Book Number. So if you look in the title page of a modern book, you'll find it's got a 13-digit ISBN, which identifies the book and the edition, I believe. And the last digit is a checksum again. So there are 12 digits, information digits in a checksum, and the checksum is calculated this way. So it's much the same. Everything's added up mod 10. We don't need to worry about a minus sign, really. Except that every other one is multiplied by 3 before being added up. Okay, let's first of all check that still does single-digit errors. So, of course, it does with one of these. If I'd mistyped that, then just as before, the checks, it's not going to check. If I mistype one of these, now 3 is carefully chosen here because remember that 3 was the number, that the multiplication table of Z10, all the numbers in the 3 row were different. And that means if I mistype D, I'm going to get a different value mod 10 here. So again, it's not going to check. So yes, it still catches single-digit errors, but now it'll also catch transposition. So supposing I were to mistype C and D the other way round, then instead of calculating C plus 3D, the website will calculate D plus 3C. And when you subtract those, you get 2 times C minus D, which is not going to be 0 mod 10 unless D minus C is 5 mod 10. So in other words, this detects all single-digit errors and all transposition of adjacent digits unless the digits differ by 5. So it won't catch 1, 6, but it'll catch lots of other things. So that's an improvement. That's good. We can do even better. So this is, if you look at an older book, they have 10-digit ISBNs. Again, there's a checksum, and it uses mod 11 arithmetic, would you believe? This is exciting. So here we go. Here are 9 information digits and the check digit, and the check digit is calculated that way. So now each number is multiplied by a different number, and then they're added up mod 11. Now, you'll spot a problem straight away that if you add up all those numbers mod 11, every now and again, the answer is going to be 10, which is not a single digit. Well, it is if you write in the Roman numerals, so that's what we do. If J turns out to be 10, it's written as X. Okay, so strictly speaking, these are not numbers anymore, because that might be next. Anyway, so let's see that this still does single-digit errors. Yeah, it does, because remember, 11 is a prime. So in the Z11 multiplication table, every row has one of each number. So if I mistype any of these, let's say D, then this will not be the same as, will change mod 11, so the check won't check. But it also does transpositions even of non-adjacent digits. So supposing I were to get C and G in the wrong order, which is, to be honest, not a very likely thing for me to do, but let's suppose I did, then the website would calculate 3G plus 7C instead of 3C plus 7G. and the difference there is 4 times C minus G. And that's not going to be 0 mod 11 unless C and G are 0, and C and G are the same. So yeah, so this detects all single digit errors and all transpositions, even of non-adjacent digits. So that's a very powerful checksum. Okay, now let's see what really happens on a bank card. So again, we've got 15 information digits and 1 check digit. And the checksum is, again, the sum of things added up mod 10. And so every other one is left alone, and the alternate ones, well, something's done to them, but it's not multiplication by 3. What it actually is multiplication by 2 mod 9, would you believe? Well, it is if it's 0 to, if A is between 0 and 8, then you just double it in Z9. If it's 9, just leave it alone. Well, sort of, I suppose 9 is congruent to double 9 mod 9. So anyway, that's what you do. So this is the table of the hatted numbers. So this up to here is the 2 row in the Z9 multiplication table. 2, of course, being co-prime to 9, and then we just leave 9 alone. So, for example, if this is our 15-digit number, we double this one, leave it alone, double this one, leave it alone, double this one, mod 9, so 5 is 1, it goes to 1, leave it alone, blah, blah. Here is one that's in a doubling position, but it's 9 to 9. Okay, now let's see how that works. So there's the formula, there's the table. So first, let's check that it checks all single-digit errors. Well, yes, it does, because so it certainly does for these ones. That's easy, isn't it? Just it's the same with all the other ones. For these ones, if you change, well, let's say A, well, you definitely change A hat, because all the A hat numbers are different. So yes, it does single-digit errors. Now, what about transpositions? Okay, so let's suppose we transpose A and B. Let's suppose, first of all, A and B are both in the range 0 to 8. So in that case, we're just doing this Z9 business. So instead of, in Z9, instead of 2A plus B, the website's going to calculate do B plus A, and the difference there is A minus B, which is not going to be 0, mod 9, and so it's not 0, mod 10 either. Okay, so that works. Of course, if A and B are both 9, then it doesn't matter swapping them. So now we're left with the case where one of them is 9 and the other one isn't. So let's suppose B is 9, in which case the correct thing is B plus A hat. Well, it's 9 plus A hat. And if you swap them, you get 9 plus A, because the 9 stays the same when you hat it. So 9 plus A hat changes to 9 plus A. But A hat is different from A unless A is 0. So this will check all single-digit errors and all adjacent transpositions except 9, 0, and 0, 9. Oh, but I didn't mention at the beginning, this is called the Luhn algorithm after the chap who invented it. Okay, so that's a pretty effective algorithm, actually. This is the earliest of these real-world checksums. It goes back to very early 50s. This whole subject is called error control codes, and it really started in the 40s. So the Luhn algorithm is a very early example. So checksums are simple forms of error detection code. That is to say, they detect errors. There are also error correction codes, which not only detect that an error has happened, but what error has happened, and therefore be able to correct it. You need more check digits for that, of course. And they're widely used in the modern world in communications and digital storage. So, for example, you may know if you scratch a music CD, unless you scratch it so badly that it'll damage the player, it's very likely to play perfectly. Not just with some degradation, but actually perfectly. And that's because the data on the disk includes some heavyweight error correction codes. So the computer inside the CD player can work out that an error has happened because of this scratch and what the error was and put it right. So the music would be perfect still. It's also widely used in communications. So supposing, for example, that we send a message around the internet, it goes from computer to computer to computer. And in each of those steps, there might be errors because of noise on the line. But again, there's powerful error correction involved. So the receiving computer will be likely to be able to detect that an error has happened and what error has happened and put it right again. so that the communication will in the end be perfect from end to end. And that's one of the key advantages of digital communications as opposed to analog communications. With an old-fashioned analog phone line, if there's noise on the line, well, there's noise on the line, and there's nothing you can do about it. With digital communications, you can restore perfection. Some of these error correction codes use finite fields, the sort of things we've been studying here. Not ZP, not those simple ones, but there are in fact more complicated finite fields, and some of those are used in some error correction codes. So there we are. That was the topic. I hope you enjoyed it. Thank you for listening.